In this video we're going to look at how we might use an additional step to increase the accuracy of our answers. This is called using a cooling curve, and it's going to account for any heat loss that occurs. So we're going to try and minimise that effect of heat loss. So what do? We put the hydrochloric acid in a polystyrene cup, same as we had been doing before. So we've put our chemical in our cup, 50 centimetres cubed, 2 moles per decimetre cubed HCl. Okay, got our thermometer in, and instead of just recording one temperature at the start, we're going to record the temperature each minute for 3 minutes. So at the very beginning, 1, 2, 3. By doing that, what you'll find is a more consistent value for the temperature of the solution at the start. So maybe it takes a little bit of time for it to come to the temperature of the room. It looks like in this data, where the chemicals have been stored has been slightly warmer than the room, so it's just cooled down ever so slightly. So you get a more accurate starting temperature. And then it says at 3.5 minutes, magnesium turnings were added. So 0.24 grams of magnesium. You're not measuring the temperature at that time because you're busy adding the magnesium and stirring. And then the temperature was taken for more minutes. It sort of depends on your results how long you would keep going, but you would try to keep going until it sort of stops changing too much. So you might do another 5, 6 readings, enough readings that you're going to be able to draw a line of best fit. So at least 4 or 5 to be able to draw a line of best fit. We've got 2 sections to this graph. We've got 2 sections to this data. We've got the first few minutes before we added the chemical, and then a series of times after we've added the chemical. Both sets of data, we've got enough points to draw a line of best fit through. So now you need to use your graph paper in your pack to plot a graph of temperature against time for this data. So we want the time along the bottom and the temperature up the side. And if you've managed that, it should look something like this. And what you want to do is take your ruler and draw 2 lines of best fit. Now the first line of best fit goes through the first 4 points and continues to the point of addition. So it needs to continue to 3.5 minutes. You need to extrapolate that line, and the second line of best fit goes through the remaining points and again continues back to the third and 3.5 minute mark. What we're trying to find out is at 3.5 minutes how big the temperature change actually was. So at the point that you added the magnesium, how big was the temperature change? And the benefit of this method is that what is actually happening is as you add the chemicals, they are releasing heat, but at the same time they're cooling down to the environment. And up here at the top, what we can see is this rate of cooling. So the room is cooler than the chemicals, and so they're releasing heat to the surroundings all the time. And by extrapolating back, we can find out what temperature they would have been at the time of addition had they not been continually cooling and heating. Now you need to be careful, this data set's really nice, it's all clean lines. If your data points had some nice lines at the beginning like that, but then it went up before it came down, then you would only be drawing a line of best fit through those that were going down, the rate of cooling. The chemicals were still warming up here, and so we don't know what's going on, so we would extrapolate all the way back and find at the point of addition how big that temperature rise was. So we will be practicing that with some questions. Okay, so if you look at your graph, it slightly depends on your graph what you got as your temperature rise. Now on my graph I got a temperature rise of 25.1 degrees C, or Kelvin, because the difference is the same in both. Our balanced equation. So see if you can write a balanced equation between magnesium turnings and hydrochloric acid. Should look like that. Okay, so let's work our steps out. Remember, step 1, Q equals mc delta T. the thermometers in the liquid, and how much liquid did we have? So we go back up, we had 50 centimetres cubed of liquid, and the temperature, I've got 25.1. Now if you've got a slightly different temperature rise there, you need to use yours. Okay, step 2, calculate moles. Okay, so the moles, and in fact we've got to do it for both to decide which one to use, don't we? So let's do it for magnesium. It's a mass over an MR, and we use 0.24 grams, and the MR is 24.3. So 9, not quite a nice number there, but not far off. Number of moles of hydrochloric acid is volume times concentration. So it was 50 centimetres cubed of 2 molar, which is 0.1. Which one of those is in excess? So you would need twice as much magnesium, twice as much acid to react with the magnesium, but even if I double this number is equivalent to almost 0.001, even if I double it I would only have 0.02, so this is the excess, which means for our calculation we use this moles. Okay, so delta H is Q over moles, remembering that Q has to get converted into kilojoules. So 5245.9 divided by the moles of magnesium, because that's the maximum moles that could react. And you get 531 kilojoules per mole. And now remember, our final step is to choose the sign, and because the temperature went up in this experiment, be minus 531 kilojoules per mole.